Well, there was a lot of mystery for me too. I work on the Evergreen Open Source Library System project, which is a project for academic libraries and public libraries to build a library system. And we've used tsearch too back when it was still just a contrib module before it was added in. And for me, it was sort of a black box. So I've been digging into it for the last, I don't know, 6 months or a year to try and find out some of the problems I've been having. And as a result, decided to try and put this tutorial together to help other people make use of it and maybe learn from some of our mistakes and get going on it. So this summer was a good opportunity because we had a student that was hired to scan all of the student newspapers at our university. I work at Laurentian University up in Sudbury, Ontario. 40 years worth of student newspapers with up to 3 different newspapers at a time. So we're getting lots of text out of that. I love students because they do things that I couldn't do. And we're going to upload those to archive.org. They're in the process of getting uploaded there, and the Internet Archive does full-text search for us. But we also wanted one locally and independent that we could tweak and use, so I wanted to build a search engine on that. So that's part of the basis for some of the examples in this. And if you go to the URL at the bottom, stuff.coffeecode.net 2012 pgopen.fulltext, you can get the raw text and the HTML and the PDF of these slides if you want to follow along or pick it up at home. So the simplistic approach that seems like everybody sort of starts with is to just do a simple like or I like or regular expression matching. Create your table that has a few text columns in it and then run selects against it with variations on those operators. That doesn't work very well. Oops, sorry. Getting used to the projector or control here. So it's got problems. If you've got just some sample data, it's not such a big deal because it can hold everything in memory and scan through that really fast. But you don't want that when you actually scale up to any sort of reasonable level of data. And index expressions can help a little bit, but in this case, you'd have to anticipate every possible query that would be coming in for your index expressions. That doesn't work all that well. There is the extension for trigrams, which is pretty cool. And you could build your own, but that doesn't make any sense because we actually have full-text search that's built into Postgres since 8.3, I believe. This has been in there for a long time. And those guys, Oleg on the left and Theodore, were kind of the core developers for that and can be thanked heavily for that. And I think Christopher Kings-Lynn wrote most of the documentation that's in the Postgres manual, which is excellent documentation. And I highly encourage it if you want to dig further into any of this. So I wanted to start out with a couple of demos. So the 2-minute demo, which you could get running fast, just as a proof of concept, I wanted to take the first 50 issues that my student had uploaded and the Internet Archive had generated the text for, load it in the table. So as you can imagine, the table that I showed before just had sort of the content text column. We create a TS vector index, and we'll talk about what these things are later, using a GIND index on it. And our search queries are very simplistic, but do the job. So we want to match the TS vector, which is a text search vector of the content, against the text search query, which is strike with a Boolean and picket to get any matches from that. If we want to get more exciting, we can add in a ranking algorithm, which says, okay, we want to get the cover density ranking for the match. And in this case, we're going to do some Boolean ORs of the terms that are coming in. Right? So this is nice, raw SQL, but it works nice and fast. So that's my 2-minute demo. So if you followed along with that, you can basically go and build text searches today. You can robotically copy and paste this and adjust it for your schema, and that'll work. But we want to do more than that. First of all, 50 rows. It's all still being held in memory, so that's not all that useful. So let's go up a little bit more to 1 million rows. So the Open Library, openlibrary.org, very generously makes all of its data underlying its 1 wiki page per book available for download on the web, so it makes for a nice, useful test data set to work with. So I grabbed that, populated 1 million rows from Open Library. There's many more, but that's good enough for test purposes. And I created, in this particular schema, I added in the weighted and unweighted TS vector columns to go along with our title and subjects. I'm using the editions of the books, which basically just gives me the title and the subjects, and then a whole lot of references to, say, author objects that don't have actual text with it. So this is the easiest way to load up the data. So once I load in the million rows, which takes about 5 seconds down at the bottom, then I'm going to set the unweighted keyword column to the equivalent of concatenating these two TS vectors together. In this case, I'm specifying a parameter to say, treat this as English text. It's not actually true in the case of Open Library. Not all the text is English. But without having any way of knowing what it is, and knowing that most of our searchers are probably going to be in English, let's go with that. We're using the standard concatenation operator. Again, a TS vector that's generated with the subjects. And in this case, not all the records actually have subjects. They might come back null, in which case we want to coalesce it to be safe. It's nice and protected. So creating the unweighted keyword column, or populating that, takes, let's see, about 40 seconds. And this is just running on my laptop. So again, lots of variation in performance as a result. Finally, we will create the weighted keyword column. In this case, we're taking the same basic expression that we had up here, but we're wrapping it with a setWeight function. SetWeight applies up to 4 different weights to the text that's coming in. And that gives us the ability to do things like rank the hits differently depending on what the weight of the indexed TS vectors were. So don't worry if this all seems very fuzzy to you. What I wanted to show primarily is that it's pretty darn fast. Again, another 40 or 50 seconds to load up, or sorry, to populate that column. And then we can actually create some indexes. So we're going to create indexes on both of those, both the title and the subject's base columns, as well as the unweighted and the weighted keyword columns that we created. And those are taking on the order of 25 seconds for each. All told, we're actually under 5 minutes to create this 1 million row example. And at the end, we actually get some pretty nice results when we're doing searches. So in this case, I'm just taking a substring of the title to make it fit on the slide. 1024 by 768 gives you some limitations. I'm doing ranking because I want to get the most relevant searches. And I'm doing this against the unweighted keyword column in this case, so we can just compare later on with the weighted keyword. Once again, I'm using the name of the TS vector. In this case, since the type of the column is TS vector to begin with, I don't have to transform it into a TS vector. Using the match operator, and we're converting our query, again, which is government and history. We need to find those two terms together. And I'm ordering it by the relevancy, so we get the top 5 hits. So for government and history, you can only see the first 20 characters, but we're not actually seeing much in the way of government or history in the title, which is kind of what you would want to probably see for a general sort of search. So we can do a weighted search instead. And all that we're doing is we're swapping out the weighted keyword column in our matches. And in this case, you can see that by saying set weight A for the weighted keyword, or for the title, and set weight D for the subjects, the weight of the title column has really jumped up the importance of seeing the terms government and history in the hits, in the rankings. So, so that's about, well, that's not about it, but that's kind of the core. Yeah, Bruce. 3 slides. Sure. Here? Yes. Sure, yeah, so just by way of explanation, you may want to search just the title or just the subjects separately. So I've created a separate expression indexes for those in that case. So the unweighted and the weighted keywords are concatenations of the two, and the title and subject are just, we just want expression indexes to stand alone for those, just for random queryability. Sure. Sure. So So I could have created an expression index that combines those two columns together without having to create an extra sort of weighted keyword column or unweighted keyword column. And I think I tried that, and I think I actually found there was a performance difference in trying it. I would need to go back about a week in time to test those out again, but if I recall correctly, that's why I chose to do the TS vector in the table itself. So again, you always want to test with your data and know that you do have the option of having expression indexes purely, or creating a column that represents the concatenation and working on that. I think it's actually a little bit expensive to do the concatenation of the two columns. So I think that might be why, because you've got to adjust the positions of all the lexemes. Anyways, we'll talk about that a little bit further on, but good question. I do encourage questions, by the way, coming through. So, and then we threw in one relevancy tweak up here. So in this case, we say, adding this 4 magically to the tsRankCD function says it's really important to get these two terms as close together as possible. And it's a cover density algorithm. And you can see in the results, we're looking at running over a million rows. We're getting our 5 rows back, relevancy ranked, at 92 milliseconds or thereabouts. Everything was consistently coming in well under 100 milliseconds, which is nice and fast. Yeah? I did not. I was purely using the default relevancy ranking threshold. I cannot recall off the top of my head what that is. Right, so there are controls, many other controls you can use to, I guess, with the relevancy ranking threshold. Is that where we're cutting off below a certain threshold any results? So if you've got the two terms, but they're at the very start of a 10,000 word document and the very end of a 10,000 word document, you could say that's not good enough for our relevancy ranking. The relevancy ranking algorithms, if you're going to step into those deeply, you need to spend some time with the math and the scoring, and I haven't spent that much time with the math and scoring to really work at that point. Yeah, Bruce?
Does our documentation cover relevancy ranking?
The documentation in Postgres does cover relevancy ranking. It covers at a very superficial level. So I actually went back to read one of the seminal papers. I work in an academic library, so I have to use the word seminal at least once in a presentation. One of the seminal papers by Charles Clark on the cover density algorithm, which talks at great length about how in 1999, when the paper was published, they had run, I think he was working at Omnitext at the time, he's a University of Waterloo researcher, the basis of the cover density algorithm. And that is a touchstone paper for a whole lot of other relevancy ranking algorithm papers. So to really get into the math and the evaluation, you probably need to go back to the source material. I don't think we get into that much depth. We have to say cover density, we say I think in the documentation we say a cover set represents the greatest distance, the minimal distance between all of the terms that are required in the query. So it's better if the three terms that you're asking for appear within 10 words of each other than if they're 100 words apart. So that's that tweak where I added the 4 is saying, give me cover density as part of the ranking algorithm. A lot of the other algorithms are mentioned just in passing, but they're things like frequency that the terms appear. So if the same terms repeat over and over again, that can increase the relevancy, but you can then adjust that via document length or the number of unique terms that appear within the document. So you can get into a whole lot of tweaking, and this final parameter is actually a bit mask, so you can apply a whole lot of different transforms to the relevancy ranking algorithm to make it do something that might be closer to what you want than just the default. But what I'm trying to say with the 5-minute and the 2-minute demo is you can get it working out of the box pretty damn well with mostly just the defaults without a whole lot of work. So if there's nothing else that you take away from today's talk and you wanted to use full text search, at this point you might be able to go away and do that. Now we can dive in a little bit further. So to step back and start talking about some of the concepts that you'll run across when you're reading the documentation or seeing some of the functions in place. To know what's going on with the full text search, we'll talk about the parsing process. So a document is really just the bag of words that's coming in. It can be a single word, it can be the title of a book, it can be the whole full text of a PDF. It's just a bag of words, undifferentiated, plain text coming in. Oops, sorry. One of these days I'll hit the right keys. So then the full text parser takes that document and splits it into tokens. And the parser is fairly rigid. It understands 23 different types of tokens, or thinks it recognizes 23 different types of tokens, and it will split them up or modify them and classify them and give them back to you accordingly. So standard things would be words and numbers it would recognize, but it recognizes some other things that might be surprising to you, like it recognizes URLs or email addresses, signed integers versus unsigned integers. And then the full text parser will apply dictionaries to normalize those tokens to create something called lexemes. And getting over the terminology in full text search was probably the hardest part that I had in getting a feeling that I had a good understanding of it. And lexemes was probably the hardest part, and that's where my patch came in, because there was one instance where it's called lexems, and that bugged the crap out of me. So we have that fixed, and a policy for backporting typo fixes in the docs as well. Yay. So yeah, some of the dictionaries, they're not just plain dictionaries like you would think an English-French dictionary would be. They do other actions like folding the case of text that's coming in, applying stemming algorithms, so recognizing things like pluralization or different forms of verbs and getting back to a root word, or using a thesaurus to, say, take two different forms of a word and just return a single word back. So a lexeme is a normalized token according to the rules of the normalization that you've applied. And then the text search data types that we deal with primarily are the TS vectors and the TS queries. In TS, it took an embarrassingly long time to figure out, oh, that means text search. So text search vectors are like arrays which contain the lexemes and also know where in the document those lexemes occurred. And a text search query, TS query, is just the text search query that's been processed so that the text search engine knows how to apply it with the match operator. So the tokens, all 23 tokens, if you really want to see them, are very easy to grab. There's really only one parser that Postgres uses, the default parser. It's possible to create your own. It's possible to customize it if you modify the source and recompile it. But otherwise, this is what you get with out-of-the-box Postgres. And like I said, it's kind of rigid, and it does some things that can be problematic down the road and have led to, I think, some of the workarounds that we've used which have slowed down our performance. Probably just by way of example, down at the bottom we have the int and unsigned int. It'll take 4 digits, a hyphen, and 4 digits and say, oh, I know what that is. That's an integer, sorry, a signed integer, and it's an unsigned integer. And it breaks it apart into the two. Except in the library world, that's an ISSN. It identifies a periodical uniquely. And there's no way of stopping it from breaking that unless you hack around it by transforming the text first. And then that introduces all sorts of other delays because you've got to do that to all the incoming text in the queries that you're doing. So you don't want to do that. So at some point, I hope to be able to work on making the parser extensible. Possibly doing some plugins or something along those lines would be, I think, fantastic.
I'm sorry, I don't know. Can you actually handle like group of characters rather than the whole word?
Group of characters. So can you explain what you mean by group of characters?
Like searching for, say, name where you know the partial characters.
Yes, prefix matching. Yeah. So if you were looking for Jignesh, and you didn't know how to spell Jignesh, whether it's J-I-G-H-N-E-S-H or J-I-G-N-E-S-H, you could say in full text search as of 9.0 in Postgres, you can apply the prefix operator, which is a colon asterisk after J-I-G if that was good enough, and that would do a search. So yes, that is supported. You want an index. Bruce?
One, just to warn you, one problem you had with extending this is that if you create an index with a given set of token rules, if you change the token rules, you effectively validate.
Yeah, you have to reindex it all. Yeah, yeah.
That's actually prevented us from improving
Right.
the fact the indexes are now never changed for many people,
Right.
it has limited us.
Right. So Bruce is saying that if you modify the text search configuration, even if you just modify the text search configuration, you have to re-index, create new indexes to correspond to it. It would be even worse if you changed the default parser, because in that case you would also have, if you created TS vector columns, you'd have to recreate all those TS vector columns as well. So there'd be a lot of pain associated with that. It wouldn't stop us from having extensions, though. If we were able to extend it and not change the defaults, then in theory there's no, yeah?
If you get PG dump of a TS vector column,
Mm-hmm.
and you load it into a new version of Postgres that had a different token rules,
Mm-hmm.
that would be an invalid.
That would be an invalid load, yes.
Even now I remember even before PG upgrade, you could not change this thing
Right.
without invalidating those dumps.
Right.
That's a great point. That was valid.
Right. Thank you for bringing that up. Yeah. And that, I think I mentioned that in passing on the way through, just in terms of changing the text search configuration. But so let's actually see some lexemes in the wild. So normalized tokens, or you can think of them as root words in some ways if you're looking at something that has a stemming algorithm in place. So just by calling to TS vector and saying this is going to be English text, we can see that we get 1973. These are coming out in alphabetical order. 1973 has position 6. It hasn't been changed at all. Breakfast has been lowercased. Champion has had its S ripped off, so it's just champion. It's now a root word. Kurt and Vonnegut just get lowercased. Same sort of thing if we take a French phrase and call it English. It just very blindly applies English rules to the French text. So en is en, les is les, nuit, it gets recognized as a plural, and that's cool. And Paris is apparently the plural of Paris. If you have a way of telling, of differentiating your text and knowing, then you can call it French, and it does the right thing. Le is the singular of les. Nuit is also singular of nuit, and Paris is maintained. En is recognized as a stop word and is thrown out by the default French text search configuration. So that's cool. I like multilingualism. I work at a bilingual university, French and English, so it's kind of important. The biggies, we've already seen 2TS vector, which gives us back, yes, question? Yes. Are stop words modifiable? Yes. In fact, on page 22 of this presentation, I have an example of how you would modify the text search configuration to get stop words thrown out. There are other ways of doing it, creating dictionaries that have additional stop words or have a subset of stop words, your own custom set of stop words, but modifying it to just say don't use stop words at all is probably the easiest way if you want to keep the classic problem of searching for to be or not to be. Question?
Yeah, you can have a column that with the data type like string or text.
Okay.
And change it to, TS vector. You need to apply extra thing.
Right. Yes. Yes. You need to convert the strings or text to a TS vector to work with the full text search. Is that? Yeah. Restating the. Okay. Yep. So we've seen 2TS vector gives us the vector of lexemes. 2TS query obviously gives us a TS query. Plain 2TS query, I think all that it does is takes a plain text string and says, let's apply Boolean ands in between all the terms within it. So not too exciting.
It's actually pretty useful. We use
Right.
plain TS query.
Okay.
We found it was easier. Usually they'll do something, you want to do some kind of testing or syntax.
Right.
It's easier just to hand it to.
Okay.
I was surprised that it did hyphenation better than we were able to do it by hand.
Okay.
And I was surprised about that.
Okay. Sorry, can you explain how plain TS query handled?
It does some kind of a normalization on,
Right.
on the query. And it does a normalization on the query. In fact, we originally
Right.
looked at it as a way of creating a normalized version of the query.
Interesting.
Headlines. But it was, I haven't looked at the code or the source code. There's not really a lot. I don't know the best way to explain plain to. It cleans up the query, basically. It cleans up the
2TS query also applies all of the normalization rules that 2TS vector would.
the main thing I noticed was hyphenation. The hyphenation
Okay.
rules got right. Before they weren't right.
I wonder whether you were getting a different configuration where it maybe avoided the hyphenation. Interesting. That's
Yeah,
we can,
we haven't done a lot of work on
okay.
investigating. I just noticed that all things got a little better, and so that
Okay.
was
Interesting.
The hyphenation was one I noticed got
Okay.
correct.
Well, that's worth looking into further, I think. Thank you. Yeah.
Actually, honestly, I hadn't used text search until this morning when I had somebody asking me about it at the client where I
Okay.
started looking into it. The plain to TS query seemed to fix it seemed to do what they were looking for, but it kind of they kind of need the stuff to be in the order it was in the original string, just normalized. It's
Okay.
weird. Does it keep? I tried like 20 or 30 different examples throughout the database, and everything came back in. This is what they're doing. They're taking video titles,
Right.
and they're making URL strings out of them, shortened, like removing all the stop words and shortening things to make a shorter URL.
Okay.
And this seems to do it.
So plain 2 TS query was essentially doing the normalization. You weren't actually using it in full text search, or
This is something they just put in.
okay.
They're just looking to do this now. So
Interesting.
they were going to be making. They had no idea this was even in Postgres. They were going to be
Right.
making their own stop words table.
Okay.
And doing joins against it and splitting their thing out into like they're doing all this manually.
Excellent. So that's an excellent.
I'm assuming that the plain case query keeps the words in kind of in the order they were in the original.
Yeah. I mean, we could try it and find out.
And I tried like
Okay. Okay. All right. Yeah.
I was wondering if you know that it's always going to do that.
I do not know offhand because I was focusing on the more complex sort of 2 TS query, trying to handle the multiple booleans and operators like this. Right. Right. Because
I just did that and then I just ran that through some string manipulation to get like a plain string back that they can use.
right, because plain 2 TS query would run it through the normalization, whether you had the default normal text search configuration or English, whatever you asked it to do, it would do. So you're getting kind of the benefits of the normalization without necessarily having to build any extra logic. You're building, yeah, that's great.
Yeah.
Great.
I'm just kind of wondering if the assumptions I made just trying it out are going to be consistent forward or.
That I can't answer, I'm sorry. Yeah. Yeah. Find out in production. All right. We've seen that match operator. There are actually other match operators that do negation, but we've been handling all of the Boolean rules within the TS query itself when we pass it in. So I've really only been using match in our production. And 2TSBug is useful for seeing what's going on when you pull in a string and you pass it against a given text search configuration. So I think this is probably what this would give you the same sort of results except more information about what's happening under the covers. So I think you're going to see you'll get those lexemes back in the same order all the time. So I think you're going to be fine. You'll just see how every piece of it's getting classified by the parser as it's coming back. And if it's getting exploded into two pieces, then why it's getting exploded into two pieces, that sort of thing. So, all right. So yes, our 3 Boolean operators, because as a librarian, I need to talk about Boolean operators. It's also a requirement for every sort of session that I give. And there's our wildcards for matching prefixes. So a few examples. These were student newspapers. So a student strike happened to be going on during the time phase that we had for that block of issues. So you get some interesting stuff. If you're interested in strikes that don't mention student, it's actually a terrible example because it's student newspapers. Every newspaper is going to have and mention of the word student, but so it gave me 0 rows back, which at least told me is doing the right thing. If we wanted to do prefix queries, we didn't know if it's professor or professional, professeur if you're using French, then you can get the prefix queries here, and we've OR'd them because it could also be faculty, could also be facility. So be careful with what you're prefixing because you might get matches for things that you don't really want, but you know, that happens. And this is about the closest to phrase matching, and this is a bit of a downfall of full text search right now that we have. So you use the text search indexes to limit the number of rows based on the terms, faculty and strike, but then you have to run it against an I-like or a like query. So that's, if I'm going to put in a sort of a downer at this point in Postgres's full text search, that's probably the closest thing to a downer that we have. So if you're trying to do an exact phrase match, the equivalent of putting in, well, actually Google doesn't do exact phrase matches anymore. So who needs them? Yeah, that's the closest that you can do. And that can be kind of slow, yes. Bruce. I do not believe there is. There's not like the equivalent of a proximity or anything like that. Yeah. So. Yes. Yeah. I was going to mention that as a possibility, but yeah, only given time, because then you're talking about extensions, and this is supposed to be for novices, so it's supposed to be. Anyways, I'm fairly confident. Yeah. The planner seems to be very smart about that. So for any given data set, it might not do that, and it might go and do a sequential scan, but you really, yeah. Yeah.
We implemented something very quickly in-house. I don't remember all the details. Remember, one of the problems we had with the planner, if we created an explicit field with the TS vector, the planner was smarter.
Mm-hmm.
And it fixed it. It was early in the development.
Okay. Better.
And I don't know the details specifically, but the implied use of the TS vector, the optimizer didn't seem to pick it up. And I think it was 9.0, but it may have been 84. I'm not
Okay.
sure. But it was, I just remember when we created a separate explicit TS vector field, they got popped into the trigger, and then we joined against that.
Right.
Against that common array.
Okay.
So it was definitely something that was kind of surprising.
And that might match my results with creating the unweighted and weighted TS vector columns explicitly versus using the expression indexes, possibly. So, but yeah, the planner always gets smarter, so it won't be a problem in the future. So normalization, yeah, planner always gets better. So the normalization, we've had a few examples of those. The normalization takes place sort of 3 steps. Well, 2 steps, really. The parser does the first level of normalization, where it may break things up and return you back more tokens than you had coming in. In some cases, I think in hyphenated words, it gives you both the hyphenated form of the word and the individual terms that appeared within the hyphenated part. And so, as I said, in practice, there's really only the default parser right now. The dictionaries are the sort of sets of logic that do the real normalization after the fact. So it can do things like pull out the stop words or unify synonyms through a synonym dictionary or do the stemming algorithms. The templates are what you would build your own custom version on. So things like a synonym dictionary, you tell it the template is a synonym, and then you apply the list of words that you want to use as synonyms. You pointed at that. I've got an example of that. And the configurations are the combination of which dictionaries to apply in what order to each token that's returned by the parser. So you can bunch these up and have a whole bunch of different dictionaries applied against each token that's coming out. The parser, I don't believe it does. The parser just says, this is a whole bunch of text, and here are the pieces, and so that I know this is an ASCII word or this is a word. And the difference there is it's either a word that's completely ASCII or it's got something outside of it. It might have Unicode characters in it. But either way, it classifies it. Those 23 token types that I showed, there probably about 6 of them are variations on ASCII word versus word, ASCII word hyphenated, word hyphenated. The text search configuration is what knows what the language is according to what you told it the language was. So there's an English stemming algorithm and a French stemming algorithm that you can apply as long as you put give it the right text search configuration. So I'm using English because I'm in the States. So stochastically gets stemmed down to stocast because the Porter snowball algorithm recognizes that icali with a Y converts it to icali with just an I, and then it says icali, I recognize that as a suffix, so I'm going to strip that off, and stocast is the result. To be or not to be, by default, you get no results back because they're all stop words. Sorry, Shakespeare. And laptopping doesn't make any sense as a word. You can't verb a noun, but I just did. And so you get laptop back because it's just blindly applying the rules. So one thing that often comes up is getting the sort of keywords and context results. The TS headline function is our friend on that side of things. So in that case, you end up having to pass in your full 2TS query request as the first parameter, or sorry, the second parameter to TS headline. You've got to give it which column or what TS vector you want to apply it against, and you can apply different sets of parameters to it. So, for example, you could say, rather than wrapping it in B and /B as the selection, you could put whatever tokens you want at the start and the end to highlight it, depending on what context you're returning this to. A lot of people do it for the web, so bold makes sense. You could add a class to it if you want to use some CSS magic. And otherwise, the search is just the same. The important thing here, though, is that, sorry, this is not a TS vector. This is the plain text coming in, because it doesn't make a whole lot of sense to search the TS vector because they're all normalized words. What you want to do is highlight the results in the actual text itself. And Jonathan was saying just before the talk that he's run into problems with this in terms of performance when he's trying to run against very large text documents like full text PDF, that he's seen performance problems. So that might be something to be aware of or keep in mind in the design of your schema. I don't know if it's possible to break things down into smaller chunks. In my case, for newspapers, it would make a lot more sense to carve up the newspapers into individual stories. It would have a title and author and the text itself, and that would probably avoid a lot of the problems and give us better relevance. So better all the way around. Yeah, yeah. Yeah, my major problem with that is that I need more student labor to do all the cutting, pasting, because I don't want to do that. Relevancy, image of match. Yes, this is a note to myself that I'm supposed to search Flickr for a Creative Commonly licensed issue of a match, or picture of a match, and put it in here. So just imagine, if you will, such an image. So we want really good matches, and there's two functions that provide ranking, both of which have exactly the same signature, and the only, I've just always used TS-RankCD because it's the cover density algorithm, and it has a paper that's easily available to find on the web that describes what it's doing under the covers. So I've got a better feeling for what it's doing. But it seems to work out of the box for us. So here's the reference to the paper that describes what a cover set is. So why you get a bump in relevance if the terms are closer together in a piece of text. Professor Charles Clark is what you want to look for. So we'll see some more examples of this in place. We have already looked in our previous examples. In our 5-minute demo, we saw the multiple columns concatenated into a single column. So we've kind of covered this a little bit, and I just talked about breaking down the title author story, so kind of preface. And we already talked about how you can concatenate the TS vectors together. Now what happens when you concatenate two TS vectors together is that all the positions in the first TS vector stay where they are. The second TS vector that gets concatenated has to have all those positions bumped by the amount that the first one contained, so that it still provides validity for the cover sets and makes sense. So that might be why the expression index may be a little bit more costly than the TS vector. I honestly don't know. That's total guess. So this is just an example, and for the sake of time, I'll skip through it because we've already seen some of that. More interesting might be the weighting. So the text search in Postgres gives us 4 separate classes that we can apply, or 4 separate weights that we can apply to a TS vector when we're creating that and populating that TS vector. Use a setWeight function to do that, and by default, they'll get this set applied to the scoring for relevancy, and it actually goes in D, C, B, A order. So A gets a 1.0 bump, and D gets a 0.1 bump in terms of relevancy. So you're really penalizing a TS vector if you say set weight to D. It's general keywords or something versus a title and author if you're looking at stories. But it's not much beyond just wrapping your existing 2TS vector calls with the set weight call. And it's kind of cool because at ranking time, you can pass in a totally different array of values and change it. So if for a given search you feel that subject is much more important than the author, then you can change the scoring accordingly. So you could potentially do something like Bruce is suggesting, where you could have a single column that represents the concatenation of everything, and just bump, say, the author score for a given query massively, and put everything else at like 0.01. I think the scale has to be on 1.0 to 0.1 though, so there's only so much you can do. But that might work for you if you're running it at runtime. Yes. Yeah, there's only 4 weights that you're given. What? So is that a correction?
No, that's correct. What I was gonna say,
Yeah.
what we did instead was we had the smaller fields like titles and things
Mhm.
like that. We used the linear matching.
Okay.
And weighted logarithmically.
Right.
For the big body of the text, there's several different ones. We weighted the bigger text logarithmically, and then the smaller text linearly, and then just sorted based on the rank. Now that came out, that worked pretty good.
Interesting. So
So we didn't, yeah, it gets too complicated with this approach.
Yeah.
You got to kind of reassemble the text, whereas
Right.
I just want to have a big attribute that has a big chunk of data in it, and a small titles or abstracts.
Right.
They have a higher weight,
okay.
and that worked out real well.
Okay. So you avoided the set weight approach entirely? Okay.
Avoided it entirely. Yeah, we
Okay.
just changed the algorithm on the weighting.
Okay.
There's only one algorithm you can do on the weighting.
Yeah. Yeah.
You can do it logarithmically and
Yeah.
and so we just tweaked that, and pretty much I think it was basically logarithmic and
Right. Were you still concatenating all the columns?
not at all.
Oh, okay. So
Assemble it in the GUI. Yeah.
okay. So okay. Okay, that makes sense.
Pretty well. That was kind of a little mini breakthrough.
So were you doing multiple queries to get the results back?
No,
Normalized?
just
Okay.
query against the title table, query against the abstract table, query against the body.
Okay. Oh, okay.
But the weighting algorithm doesn't use the.
Okay.
It uses the logarithmic on
Sure.
the big body. And they're all PDFs,
Right.
Google documents. They're all kind of roughly the same size.
Okay.
But the body is weighted. I think it's logarithmically, but and then the title and the abstract are weighted at the same
Right.
rate. We just sort the.
So you're going to give the intermediate talk on full text search next year, right? Okay. All right. So here's the payoff in terms of the stop words, the question that was asked before. And this question actually came up on the Postgres channel in IRC earlier today. And a person said, isn't there an easier way to allow stop words, just like setting a flag in some config file to true or false? Although Postgres.conf is huge, it does not have a flag for stop words on and off in the full text search. And I actually like this better because it's dynamic. You can create your own configurations, restore them, et cetera. So it's maybe a little bit less flaky than having to deal with that. So all that we do is start by creating our own dictionary, which we build on we still want the snowball porter algorithm for stemming. So we say the template is snowball and the language is English. And we create a new text search configuration, which remember is a combination of the dictionaries that we're applying in order to the parser tokens. And we start by copying the existing English one. And the English one applies the stop word dictionary along with the snowball dictionary. So we then alter our text search configuration because we just currently have a copy of the default English one. And we say for the ASCII words, the ASCII H words, the H words, anything that has word in it, we just want to apply our particular text search dictionary, which is just the snowball stemming. So we still can do, once we do a TS vector call and we pass in our own brand new search configuration, we can still do a search on to be or not to be and we get what we expect back. But if we had plurals or anything else, different verb forms in there, those would be stemmed as we would expect them to be as well. So, so this is, I think, not all that bad, and this is what I pointed the guy to in IRC, and Actually, I had pointed him at it before, and then he came back and said, but isn't there just a flag I can set? So, sorry, no. So Gin ingest, I don't know, I've read it many times. Performance-wise, in theory, Gin should be better for performance, but slower building. On the scale of data that I'm working with, I don't see a huge difference either way. So other people who deal with a lot more scale might see something. I've just used Gin by default at this point because I can wait for the build time, whatever cost there is. It's probably in like the order of seconds for me, so not a big deal. But bear that in mind if you've got a massive amount of data. So as a rule of thumb, I was suggesting one index per column of interest, and then a general index, but then I'm looking at sort of a library kind of application where people want to have discrete queries against individual parts of the metadata that they're looking at. So that'll depend on your application. Yeah, Bruce?
Just to clarify the Gin, basically it's not so much initial build time, it's also the issue of if you have a dynamic
Right.
index that's getting updated every time somebody does an insert or an update,
Right.
that would be more sensitive.
Okay. Okay, so on an active table, that would more, yeah.
Most people don't have active tables put together, and it's gotten better over time. There was a batching algorithm that was added in 8490.
Okay.
So you basically now, when you do an insert, it goes into like a holding area, and then as soon as that holding area fills up, there's something that triggers a load into the main table. You still search both of them.
Okay.
When you do the search, but
Okay.
it basically buffers the loads because the sort of load algorithm just wasn't
Right.
as fast. But that's gotten so much better that I think you're right. Most people just use Gin now. Is really they've optimized Gin so much.
Right.
It just doesn't seem like.
Yeah, the strategy sounds similar to me in some ways to the Solr indexing strategy where they'll have the sort of monolithic index and then the built index, and every once in a while that gets wrapped back into the main one. So there are built-in trigger functions that you can use to maintain indexes on, maintain a TS vector column based on one or more text columns. Either one of these. The second one is kind of nice because if you are differentiating between types of data, say for text search configurations, you can tell it to use a different configuration per row that comes in. So French English is probably the easiest example for that. So there's not too much of this. I'm sure you've all created triggers before, so in the interest of time, I'll gloss over it fairly quickly. But so this is the hack I was talking about, some of the things that we look at having to do within our project to deal with the sort of limited parser. So as long as you're consistent with doing the same thing to the queries that are coming in as you're doing to the text that's getting stored, it can work, but it might have performance implications. So one of the things that happens out of the box is that the parser will recognize term 1, term 2, and say, that's a file path. So I'm just going to give you back term 1, term 2, and that's great. But you actually might want to search term 1 or term 2 independently. It might represent some other and/or, and you might want to search for and or in that case. So a terrible hack would be to pass in a regular expression that splits it up, maintains the slash form of it, but splits it up as well before it gets into the parser so that you get the original file back plus the 2 numeric words, which you can see down at the bottom here. But yeah, be aware of the implications of that. And I have an example of synonyms via dictionary. If you wanted to add, say, I live in Canada, so I deal with a whole lot of Americanized English versus British English versus French. So, and it kind of surprises me there's not something currently in Postgres that handles this. Stemming algorithms don't really apply for this. Just the additional U's that we have in Canada can be a problem if you're trying to search a large body of text and having to search twice. So you can laboriously create a separate synonym file. Another option might be you can use things like iSpell dictionaries, which might apply some of those. Although in what I found in the examples, they were either English UK or they're English American, and they didn't actually do a synthesis of the two. So this is a problem area that still needs to be solved, I think, in a more generalized fashion, because it's crazy for everybody to have to do this themselves. You could run a regular expression just to OU to O every time. You don't want to do that. All right. And this is all bonus material anyways, but you could use the Postgres trigram extension if you wanted to do spell checking. Could come in very handy if you have 0 hits for something that somebody entered. It's possible that your text doesn't actually contain the results. It's also possible that they just mistyped something. So the trigram extension is really cool because it breaks all the text that comes up into 3 character chunks, and then it just does a similarity match. If you call it, it'll do a similarity match of the incoming text that's been parsed into trigrams against the index and give you the nearest results. So, and again, you can use the either a gin or a gist index for this purpose down at the bottom. And if we wanted to create it, tstat gives us just the lexemes that are coming in with some of the statistics. We just want the words because we just want the distinct list of words. Yep.
You periodically run TS-stat because you're curious about what are common words.
Yeah, not that much, to be honest. Yeah.
Kind of interesting when you do it. So
Right. You're a text search geek, aren't you? That's okay. That's all right. That's all right. Yeah. So just to kick that example in, that operator got horribly mangled by the my HTML generator. Anyways, you can see the operator in the example. It's just the less than dash greater than sign calculates the distance between the incoming word or phrase that you gave to it and the matches that it found within the. I guess we're really only looking at one word at a time. So that is, well, that's the distance. So that's the issue, or sorry, the equivalent of a relevancy ranking. So a distance of 0 is perfect because it's the same word. Whereas if you've got a differentiation by an additional character or a substitution of a character, that's going to mean that it's further from a match. Right. Yes. Yeah. Yeah. So, and packet and pocket would have been further on down. I just showed 5 rows for the sake of not wanting to run off the list. But yeah, building something like a spell checker using the trigram extension seems very possible. It's not something that we're using currently. We're actually using a terrible A-spell approach, which throws back spelling suggestions which may not actually be in the database. So this would be a far better approach for us to use in our project for spell checking. Dimitri? Right, right, yeah. So auto-completion is another example of where trigram would come in very handy. And yeah, we have auto-completion at this point that's working. It's not using trigram, so I'm kind of suspicious about its possible performance. But
From some experience using trigram,
Mhm.
the smaller your words are, the much better performance. So actually,
Right.
I was doing something where I later switched to full text search because I was looking over, let's say, sentences, and
Right.
I wasn't getting the results I wanted. And then by going to full text search, I got things that were much more relevant.
Okay. Okay. Right, yeah, I can see. So you're looking for a full sentence to try and match? Yeah, that makes perfect sense. I think trigram is really looking at single words primarily, right? I mean, yeah.
Things that are small.
Yeah, yeah.
Where small is a relative term.
Right, right, okay. Okay, great. So I am past the 10 minutes or so that I wanted to leave for people to get to sort of the wrap for today, and I think we've got lightning talks, but I'm happy to take questions, further questions or whatever from there. And I'll point to a couple of the articles that you might want to dive into further if you want better understanding of stemming and cover density. But sure, question.
So this may be an easy question, but what happens if the encoding installation of the database changes? You already have the search code. Do you have to rewrite your search code? Say you change from ASCII to Unicode or the other way around?
I don't think I'd be capable of putting together a coherent answer on the spot because I haven't considered that scenario.
Okay, yeah,
Yeah.
just curious because other clients do sometimes
Change collations,
yeah,
just,
for performance reasons, they'll change
okay.
it to ASCII because they don't think they'll ever actually be
Right.
encoded, or for sanity reasons, they'll change it to ASCII to be encoded.
Right. So certainly for text search performance, I think out of the box, we're always using C as our locale. Even though we have Unicode data, we're using C as the locale because we don't care all that much about the collation because we've got such a mix of languages in it. But the performance of the text search function seems to be far better in the C locale than, say, if you've got ENUS UTF-8 or something. So I will take your question like a politician and return a different answer. Yeah, absolutely. There we go. Stuff.coffeecode.net. I have yet to come up with a better description of that host name, but Bruce.
Hey, for the organizers, want this put up on the website?
Yes, so there, Selena has created a wiki page in the Postgres wiki that includes all of the presentations, and all of the presentations are supposed to be linked to or uploaded by the authors. So if I've already linked this, I linked it before the presentation, so I'm a good good presenter. But if you see some bad actors out there, tap them on the shoulder and ask them to link it up.
So, have you played around with the Sphinx indexing function at all?
Sphinx is one that I've not used. I've used Solr in the past, primarily. So Sphinx, would you like to talk about it?
I haven't played with it in a while.
Okay.
So Sphinx actually, it's basically all it does is full text search, and it actually you can plug it right into Postgres. I mean, it's an external program that's running. The one thing about Sphinx is that it's incredibly fast. You do a search, and like you could have millions of rows, and it would return it in a millisecond. The older version of Sphinx, you paid a penalty because you had to every time you updated your data, you had to rebuild it. So if you're frequently updating data, it just didn't make sense. The newer version, I believe they have something called Delta Update, where you can, it basically, it'll update your indices as you go along. I'm not sure what the time penalty is, which is why I was curious if you played with it. But
Sphinx have to return all the master data set or the ID on the master data set, and then you subset it down, or is it integrated tightly into what happened?
so it's not integrated. It basically it's standalone, but it can pull directly from Postgres. So Sphinx, it works both with Postgres and MySQL. So it's ultimately, in the case of MySQL, it's like it's pulling everything in. I think Postgres it can like manipulate cursors and just get things in.
If I want to do like a query, give me everything it matches to Word since a week ago, it would have to pull everything from the whole database in, and then you'd subset it down to a week.
Yes. So you can basically choose like what queries that you want to put into it initially, or just load everything in, and then you basically build the rules within Sphinx, and then you do searches based on that.
Right. Yeah, so one of the reasons I wanted to give this presentation was to provide enough of an overview of how full text search works within Postgres so that it could be your first option. You get all the advantages of backup, synchronized data, all of that great stuff. There are some limitations for sure. Sphinx, I have heard a number of times and know people have used it. Solr I've used myself. Elasticsearch seems to be another one. If you're looking at, if you're okay with picking up the cost of also having the admin overhead and sort of having to build the understanding of how a separate product works, then yeah, those are, I think, all very reasonable options to go with performance and quality-wise. All right, everybody ready to go out and build some full text search? All right.